You trust your eyes. You trust that when you look at your hand, it's actually there. That the chair you're sitting in exists whether you're looking at it or not. That the universe carries on, solid and dependable, even when you close your eyes to sleep. You believe, because you have to believe, that reality is real. But there's an experiment, a simple experiment. 2 slits in a piece of metal, a beam of light. And the results of this experiment have been reproduced thousands of times in laboratories across the world for over 200 years. It has been performed with light, electrons, neutrons, atoms, and molecules. It has been performed in basements and on mountaintops, in vacuum chambers and in outer space. And it says you're wrong. It says that when no one is watching, the universe doesn't bother to decide what's real. That matter itself exists as a ghost, a probability, a smear of possibilities, until the moment you look. Scientists have known about this for over 100 years. They've verified it thousands of times with increasingly sophisticated equipment at scales ranging from single photons to molecules containing thousands of atoms. The math is unambiguous. The results are consistent. There is no doubt that this is how nature works. And here's the part they don't tell you in the science documentaries. Here's the dark secret buried in the data. It's not just light that does this. It's not just electrons. It's not just atoms or molecules or mechanical oscillators. It's everything that obeys the laws of quantum mechanics, which, as far as we can tell, means everything, period. The entire universe runs on quantum rules. The classical world we see is just the surface, of foam riding on an ocean of quantum possibility, including you. In 1801, a young English physician named Thomas Young stood before the Royal Society in London and presented a paper that should have ended the debate about the nature of light forever. For over a century, scientists had argued, was light made of particles, as Isaac Newton believed, or was it a wave, as Christian Huygens proposed? Newton's authority had dominated the debate for generations. His Optics, published in 1704, argued that light was made of tiny corpuscles, particles that traveled in straight lines and bounced off mirrors like tennis balls off a wall. The evidence seemed compelling. Light cast sharp shadows. It didn't bend around corners the way water waves or sound waves do. It behaved, to all appearances, like a stream of particles. But Huygens had a different view. In his treatise on light, published in 1690, he argued that light was a wave in an invisible medium, what scientists would later call the luminiferous ether. Waves could explain reflection and refraction. They could explain the beautiful colors in soap bubbles and oil slicks, but they couldn't explain the sharp shadows that light cast, or why light traveled in straight lines. Young thought he had the answer, and he was right, but he couldn't have known that his elegant little experiment would eventually shatter our understanding of reality itself. Young's apparatus was simple, almost laughably so. He took a beam of sunlight, passed it through a tiny hole to make it coherent, then directed that light toward a barrier with 2 thin slits cut into it. Behind the barrier, he placed a screen. What he expected to see, if light were made of particles, was simple. 2 bright lines on the screen, one behind each slit, like throwing sand at a wall with 2 gaps in it. The sand goes through the gaps and piles up in 2 strips on the other side. But that's not what Young saw. Instead, the screen displayed an intricate pattern of alternating bright and dark bands, what physicists call an interference pattern. This pattern is the unmistakable signature of waves. Think of dropping two stones into a still pond. The ripples from each stone spread outward, and where they meet, they either combine to create bigger waves or cancel each other out entirely. The interference pattern on Young's screen proved that light was spreading out from both slits as waves, overlapping and interfering with each other on the way to the screen. Case closed. Light is a wave. Young had done something remarkable. He had taken one of the oldest debates in physics, a debate that dated back to Newton and Huygens in the 17th century, and settled it with an experiment so elegant that it could be replicated by anyone with a candle, a card, and a wall. But there was something strange about Young's result, something that wouldn't become apparent for another century. The interference pattern he observed depended critically on one thing. The light had to be coherent. The waves from both slits had to be in phase, their peaks and troughs aligned. Young achieved this by first passing his sunlight through a single slit, which acted as a filter, selecting only light waves that were traveling in the same direction. Without this coherence, the interference pattern would wash out. Random light, with waves pointing every which way, would just produce a blur. The pattern required order. It required the light to know something about itself. But at the time, no one thought much about this. Light was a wave in the ether, and waves could be coherent or incoherent. It was a technical detail, nothing more. For nearly a century, this was the accepted truth. Light waves spread through an invisible medium called the luminiferous ether, just as sound waves spread through air and water waves spread through water. James Clerk Maxwell unified electricity and magnetism into a single theory and showed that light was an electromagnetic wave. Physics students learned it. Textbooks taught it. The universe made sense. Then, in 1887, Albert Michelson and Edward Morley performed an experiment that should have detected the ether. They failed. The ether didn't exist. Light waves apparently didn't need a medium to wave through. This was strange, but physicists adapted. Maybe light was a different kind of wave. But then came the 20th century, and everything fell apart. In 1905, Albert Einstein published a paper explaining something called the photoelectric effect, the observation that light shining on certain metals can knock electrons loose. The strange thing was that the energy of these electrons didn't depend on how bright the light was, but on its color, its frequency. Brighter light knocked out more electrons, but each electron had the same energy. This made no sense if light was a continuous wave. Einstein proposed something radical. Light comes in discrete packets of energy, little bullets of light, which we now call photons. The energy of each packet depends on the light's frequency, which is why blue light can knock electrons loose, while red light cannot, no matter how bright you make it. This was particle behavior. Light wasn't just a wave. It was also somehow a particle, and that should have been impossible. How can something be both a wave and a particle? These aren't just different descriptions. They're mutually exclusive categories. A wave is spread out, extended through space, capable of interference. A particle is localized, a point, traveling along a definite path. You can't be both at once. That's like saying something is both completely wet and completely dry. The crisis deepened in 1923 when Arthur Compton demonstrated that X-rays bouncing off electrons behaved exactly as if they were particles colliding with other particles. The X-rays transferred momentum to the electrons in discrete chunks, just as one billiard ball transfers momentum to another. The wave picture couldn't explain this. Only particles, photons, could. Compton won the Nobel Prize for this discovery. The photoelectric effect and the Compton effect together proved beyond doubt that light, under certain circumstances, behaves as a stream of particles. And yet Young's experiment proved beyond doubt that light, under other circumstances, behaves as a wave. Both were true. Both were real. Both were verified by careful, repeatable experiments. The foundations of physics were crumbling. Then came Louis de Broglie, a French aristocrat who was supposed to be studying history. In his 1924 doctoral thesis, de Broglie proposed something audacious. If light waves could behave like particles, perhaps particles could behave like waves. Every particle, he suggested, has an associated wavelength. The heavier and faster the particle, the shorter the wavelength. For everyday objects, baseballs, cars, people, this wavelength is so incredibly tiny that it's completely undetectable. For a baseball thrown at 100 miles per hour, the de Broglie wavelength is about 10⁻34 meters, roughly 1 billion trillion times smaller than the nucleus of an atom. No experiment could ever measure such a thing. But for very light particles moving slowly, the wavelength could be large enough to observe, and electrons, de Broglie calculated, should have wavelengths comparable to the spacing between atoms in a crystal. The physics community was skeptical. Einstein, when he saw de Broglie's thesis, called it a first feeble ray of light on this worst of our physics enigmas. But within 3 years, de Broglie was vindicated. But light didn't care about our categories. This was the first crack in the comfortable lie. The real terror didn't arrive until physicists turned from light to matter itself. Because in 1927, something happened that should have been front-page news, but instead was buried in academic journals, discussed only in physics departments, and slowly, reluctantly, accepted by a community that didn't quite believe what it was seeing. Clinton Davison and Lester Germer, working at Bell Labs in New Jersey, fired a beam of electrons at a nickel crystal. What they observed was an interference pattern, the unmistakable signature of wave behavior. George Paget Thomson, working independently in Scotland, found the same result. Electrons were waves. Let that sink in. Electrons, the tiny particles that make up the shells of atoms, the things that carry electrical current through the wires in your walls right now, the fundamental constituents of all the matter you have ever touched, tasted, seen, or imagined. They're waves, or rather, they can be waves, under certain conditions, when they feel like it, when no one is looking. The implications were staggering. If electrons were waves, then the orbits of electrons around atomic nuclei weren't orbits at all. They were standing waves, like the vibrations of a guitar string, the specific energy levels of atoms, the discrete colors that elements emit when heated, the chemistry of everything. These were explained by the wave nature of electrons. Erwin Schrödinger developed a wave equation to describe these matter waves. His equation worked beautifully, predicting atomic spectra with incredible precision. But what exactly was waving? Schrödinger originally thought his waves were real, physical things, smeared out electrons spread through space. Max Born saw it differently. In 1926, Born proposed that the wave function didn't represent the electron itself. It represented the probability of finding the electron. The square of the wave function at any point gives the likelihood that if you measure the electron's position, you'll find it there. This was deeply strange. The electron wasn't spread out through space, but our knowledge of the electron was spread out. Before measurement, we couldn't say where the electron was, only where it might be. The wave function was a description of our ignorance, not of physical reality. Or was it? And this is where the double slit experiment becomes something else entirely. This is where it stops being a curiosity about the nature of light and becomes a direct assault on everything you think you know about reality. Take those two slits. Instead of shining light through them, fire electrons at them. Not a beam, just individual electrons, one at a time, like throwing microscopic baseballs at a wall with two gaps in it. What do you expect to see? Each electron should go through one slit or the other. It should hit the detector screen behind the slits and make a single dot. After firing thousands of electrons, you should see two clusters of dots, one behind each slit, just like the sand, just like baseballs. But that's not what happens. Fire one electron. It goes through. A single dot appears on the screen. Fire another dot. Keep firing, one at a time. Wait between each one if you want. Make absolutely certain there's only ever one electron in the apparatus at any moment. And slowly, dot by dot, an interference pattern emerges. Bands of many hits, alternating with bands of almost no hits. The exact same pattern you'd get if the electrons were waves passing through both slits simultaneously and interfering with each other. But you're firing them one at a time. There's only one electron in the apparatus. There's nothing for it to interfere with, except itself. This was first demonstrated conclusively in 1974 by Pier Giorgio Merli, Gianfranco Misseroli, and Giulio Pozzi in Bologna, Italy. Then again in 1989 by Akira Tonomura and his team at Hitachi in Japan, who built an elegant version of the experiment that has since been seen by millions. In Tonomura's experiment, electrons were emitted so slowly, fewer than 1,000 per second, that there was never any chance of two electrons being in the apparatus at the same time. The detection screen recorded each electron as a distinct point of light. Watch the experiment run, and you see what looks like random static, dots appearing here, there, everywhere. The first few hundred electrons look like noise, random, meaningless. There's no pattern, no order, just points of light scattered across the screen. If you stop the experiment here, you'd conclude nothing. But keep watching. Let the electrons accumulate. After 10 minutes, you start to see something. Faint stripes, barely visible. After 20 minutes, they're unmistakable. The interference pattern, clear as daylight. Bands of brightness alternating with bands of darkness. Each electron arrived as a particle, a single, localized dot on the screen. But the pattern they collectively formed was the pattern of a wave, as if each electron, in the moment before detection, was spread across the entire apparatus, passing through both slits, interfering with itself, and then collapsing to a single point only when it hit the detector. The experiment has been repeated hundreds of times. In 2012, researchers at the University of Nebraska-Lincoln built a version using 62 nanometer-wide slits and a multi-channel plate detector, capturing the buildup of the interference pattern in real time. The result was the same. It's always the same. Each electron, traveling alone through the apparatus, somehow passed through both slits simultaneously. Each electron, a particle, a localized object with a definite position, somehow behaved as a wave spread across space. In 2002, Physics World magazine asked its readers to vote for the most beautiful experiment in the history of physics. The Double Slit Experiment with electrons won. It beat out Newton's prism experiments, Galileo's inclined plane, Rutherford's discovery of the nucleus. The most beautiful experiment, and also the most disturbing. Richard Feynman, perhaps the greatest physicist of the 20th century, was obsessed with this experiment. In his famous lectures on physics, he said it contains the only mystery of quantum mechanics. Everything else, he argued, can be understood once you truly grasp what the double slit experiment is telling us. He called it a phenomenon which is impossible to explain in any classical way, and which has in it the heart of quantum mechanics. But here's what Feynman didn't emphasize in his lectures. Here's what gets glossed over in popular accounts. Here's the dark secret that sits at the center of this mystery. The interference pattern only appears when you don't look. Suppose you want to know which slit the electron went through. This is a reasonable desire. After all, we just watched individual electrons hit the detector screen. Each electron must have gone through one slit or the other, right? Both slits are open, so it went through the left one or the right one. We just want to know which. So you set up a detector. It doesn't even have to be sophisticated. Any kind of measuring device that can record which slit the electron passed through will do. A photon counter, a magnetic field sensor, anything. You run the experiment again. This time, you're watching. For each electron, you record left slit or right slit. You keep track. And after thousands of electrons, you look at your detection screen. The interference pattern is gone. Where there were bands, bright and dark, the unmistakable signature of wave behavior. Now there are just two blobs, two clusters of hits, one behind each slit. Exactly what you'd expect if the electrons were particles passing through one slit or the other. The moment you looked, the moment you measured, the electrons stopped being waves and became particles. This is not a matter of disturbing the electrons. You might think, well, obviously, if you shine light on the electron to see which slit it goes through, you're going to knock it off course. You're interfering with the experiment. And early physicists thought the same thing. Niels Bohr had a famous debate with Albert Einstein about this very point. Einstein was convinced that quantum mechanics was incomplete, that there must be some deeper reality underneath all this probability and uncertainty. At the 1927 Solvay conference, Einstein proposed a thought experiment. What if you could weigh the wall with the slits? When an electron passed through, it would impart a tiny momentum to the wall. By measuring that momentum, you could determine which slit the electron went through without disturbing the electron itself. Bohr stayed up all night working on the problem. By morning, he had the answer. Einstein's proposal wouldn't work. To measure the wall's momentum precisely enough, you would have to give up knowledge of the wall's position. The uncertainty in the wall's position would smear out the interference pattern, just as surely as directly measuring the electron's path. The Heisenberg uncertainty principle guaranteed it. There was no way to cheat. You could measure position or momentum, never both. You could know the interference pattern or the which path information, never both. But this explanation wasn't quite right either. It implied that the interference pattern disappeared because measurement disturbed the electron. That's not what's happening. But it's not that simple. Because the interference pattern doesn't just disappear when you actively probe the electrons. It disappears when information about their path becomes available, even if you never actually access that information. There's a beautiful experiment that demonstrates this, sometimes called the quantum eraser. It was proposed by Marlon Scully and Kai Druhl in 1982 and has been performed in various forms many times since. Here's how it works. You mark the electrons, not by disturbing them, but by entangling them with something else. A photon, say. When an electron goes through the left slit, it emits a photon with one polarization. When it goes through the right slit, it emits a photon with a different polarization. The photon carries the which path information, but you don't have to look at it. Run the experiment. The interference pattern vanishes, even though you never measured anything about the electron directly, even though the electron itself was never disturbed. The mere existence of the which path information recorded in the polarization of a photon you never looked at was enough to destroy the interference. Now, for the twist. Take those photons and erase the information they carry. Pass them through a polarizer that mixes the polarizations, making it impossible to determine which slit the electron went through. Now look at your detection screen. The interference pattern comes back. Not on its own. You have to correlate the electron hits with the erased photons to see it. But it's there. By erasing the which path information, you restored the quantum behavior. In the most sophisticated versions of this experiment, physicists have set up detectors at the slits but never looked at the results. They stored the which path information on hard drives and then destroyed it, unread. And still, the interference pattern vanished. The mere possibility of knowing, even if no one ever did know, was enough to destroy the quantum behavior, as if the electron knew it could be caught. This is the observer effect in its purest, most disturbing form, and it has been confirmed by experiments so carefully designed that there is no room left for doubt. The 1998 experiment by Bucks, Schuster, Heiblum, and colleagues at the Weizmann Institute demonstrated this with exquisite precision, showing that the more which path information you gather, the more the interference pattern fades in exact mathematical proportion. It's not just that measurement disturbs what's being measured, though of course it does. It's that the very existence of information about the system changes how the system behaves. The electron seems to know whether it's being watched, and this raises a question that has haunted physicists for 100 years. What counts as watching? What counts as measurement? Does the detector have to be turned on? Does someone have to look at the results? Does a conscious mind have to be involved? The physicist John Archibald Wheeler pushed this question to its most extreme conclusion. In the late 1970s and early 1980s, he proposed a series of thought experiments, which have since been performed in laboratories, that made the situation even more disturbing. What if you delay the choice? What if you decide whether to measure the electron's path after it has already passed through the slits, but before it hits the detection screen? Wheeler's delayed choice experiment sounds like it should produce a paradox. If the electron has already gone through the slits, surely it has already decided to be a wave or a particle. You can't change the past, but that's exactly what seems to happen. In 2007, Alain Aspect and colleagues at the Institut d'Optique in France performed Wheeler's delayed choice experiment with single photons using beam splitters instead of slits. they made the choice of whether to measure which path information randomly after the photon should have already committed to one path or another. And the results were clear. The photon's behavior depended entirely on whether the measurement was made, even though the measurement was made after the photon had already traversed the experimental setup. The experiment has since been extended to atoms. In 2015, Andrew Truscott and colleagues at Australian National University performed a delayed choice experiment with helium atoms, using laser pulses instead of physical slits. They made their choice of measurement using a quantum random number generator, ensuring that no information about the choice could have reached the atom before it made its decision. And still, the atom's behavior was determined by the delayed choice. In 2017, a team at the Matera Laser Ranging Observatory in Italy extended Wheeler's experiment to satellites. They bounced photons off a fast-moving satellite equipped with retro-reflecting mirrors, making the delayed choice while the photons were traveling thousands of kilometers through space. The quantum wave particle duality was confirmed at this unprecedented distance. And in 2019, researchers pushed even further. They performed Wheeler's delayed choice experiment with photons that had been emitted from a source and then split along two paths that eventually recombined. The choice of whether to observe wave or particle behavior was made after the photon had already been detected, after it had already hit the screen. The correlations still worked. The math still held. This is not science fiction. This is established experimental fact. The photon didn't travel back in time to change its behavior. That would violate special relativity. Instead, the results suggest something more unsettling. The photon's past was simply undefined until the measurement was made. It wasn't a wave that became a particle, or a particle that became a wave. It was neither a superposition of possibilities until the moment of observation forced it to have a definite history. Wheeler himself put it starkly. We have no right to say what the photon is doing in all its long course from the source to the screen. Until we make the measurement, the question is meaningless. He went further, applying this logic to the entire history of the universe. Imagine light from a distant quasar, bent around a galaxy by gravitational lensing on its way to Earth. The light left the quasar billions of years ago, long before Earth existed, before the solar system formed, before our galaxy took its current shape. But whether that light traveled as a wave taking all paths or as a particle taking one path is not decided until we choose how to observe it, here, now, today. Wheeler called this the genesis by observership. Our observations today help determine what happened in the past, not by changing anything that already happened, but by making definite what was previously indefinite. The universe's history, in some sense, is not fixed until we observe it. Think about what that implies. The double slit experiment doesn't just apply to photons and electrons. Over the past few decades, physicists have demonstrated interference with larger and larger objects, pushing the boundaries of quantum behavior into territory that feels deeply uncomfortable. In 1999, a team led by Anton Zeilinger and Marcus Arndt at the University of Vienna performed the experiment with buckyballs, molecules of carbon-60, shaped like tiny soccer balls. Each buckyball contains 60 atoms. It's visible in an electron microscope. Its diameter is about 0.7 nanometers, nearly 500,000 times larger than a proton. And yet, when fired one at a time through a diffraction grating, the buckyballs produced an interference pattern. Each buckyball, traveling alone, passed through multiple slits simultaneously. The Vienna team sublimated fullerene powder in an oven at about 900 Kelvin and passed the resulting molecular beam through a diffraction grating with 50 nanometer wide slits. They detected the buckyballs using a laser ionization technique. And there it was, the unmistakable signature of wave behavior, a soccer ball-shaped molecule of 60 carbon atoms interfering with itself. The researchers confirmed that the pattern couldn't be explained by the molecules interacting with each other. The beam was so dilute that only one molecule was in the apparatus at a time. They also checked that environmental interactions, spontaneous emission of photons, collisions with residual gas molecules, couldn't explain the results. The buckyballs were genuinely behaving as quantum waves. Since then, the record has been broken repeatedly. In 2011, the Vienna team demonstrated interference with molecules containing 430 atoms. In 2013, they observed interference with molecules containing 810 atoms, objects with a mass of over 10,000 daltons. In 2019, they pushed it to molecules with over 2,000 atoms, objects with a mass of 25,000 daltons, comparable to small proteins. The molecules used in these experiments are bizarre creations. Functionalized oligoporphyrins with perfluoroalkyl chains, synthesized specifically to be volatile enough to form a beam, while being massive enough to push the limits of quantum behavior. They have names like C7097H260F, 08N, 6SS53, ZN4. They look under a microscope like complicated three-dimensional scaffolds of atoms, and they interfere with themselves. Where does it stop? The standard answer is decoherence. As objects get larger, they interact more with their environment. Photons from the room scatter off them. Air molecules collide with them. These interactions carry away which path information, effectively measuring the object's position moment by moment. The larger the object, the faster decoherence destroys quantum behavior. This is why you don't see interference patterns when you throw baseballs. The baseball is constantly interacting with trillions of air molecules, photons, and particles from your hand. Its path is continuously measured by the environment. There's no opportunity for quantum behavior to manifest. But here's the thing. This isn't a fundamental limit. It's a practical one. In principle, if you could isolate a baseball perfectly from all environmental interactions, place it in a perfect vacuum, cool it to absolute zero, shield it from all radiation, it would obey the same quantum laws as an electron. It could pass through two slits simultaneously. It could interfere with itself. This has been demonstrated with increasingly macroscopic objects. In 2010, Aaron O'Connell and colleagues at UC Santa Barbara put a tiny mechanical oscillator, a piece of metal visible to the naked eye, into a quantum superposition. It was both vibrating and not vibrating at the same time. The object contained about 10^14 atoms, making it the largest quantum superposition ever observed at that time. The team achieved this by cooling the oscillator to near absolute zero, about 25 millikelvin, and isolating it from environmental noise. At these temperatures, the thermal vibrations that usually mask quantum behavior disappear. The oscillator was in its quantum ground state, the lowest possible energy configuration. By hitting it with a carefully calibrated microwave pulse, O'Connell created a superposition of vibrating and not vibrating. The superposition lasted for about 6 nanoseconds before decoherence destroyed it. 6 nanoseconds isn't long, but it was enough. The laws of quantum mechanics applied to an object visible without a microscope. Since then, larger and larger objects have been coaxed into quantum superpositions. In 2016, researchers in the Netherlands put a small tuning fork into a quantum state. In 2019, a team in Vienna demonstrated quantum interference with molecules containing about 2,000 atoms. Each year, the boundary is pushed further. The theoretical physicist Roger Penrose has proposed that gravity itself might cause wave function collapse, that a superposition of two different mass distributions creates a superposition of two different space-time geometries, and this cannot be sustained. According to Penrose's theory, there is a fundamental limit to quantum superposition, set by the point where gravity becomes important. For a buckyball, this limit is far beyond what current experiments can probe. For a human brain, it would be astronomically short, trillions of times shorter than we could ever measure. But Penrose's theory hasn't been tested. It's one possibility among many, and it still wouldn't explain why measurement collapses the wave function, only what causes spontaneous collapse in the absence of measurement. The physics is clear. There is no boundary. There is no scale at which classical physics takes over and quantum mechanics stops. The boundary is not in the physics. It's in the environment. It's in information. And we are made of atoms. This is the part that nobody wants to talk about. This is where the popular science books wave their hands and move quickly to the next topic. Because the implications are too strange, too unsettling, too incompatible with how we experience the world. If electrons, photons, buckyballs, and vibrating metal strips can exist in superposition, can be in multiple states at once until observed, then why not you? The atoms in your body obey the same quantum laws as the electrons in Young's Double Slit Experiment. There's nothing special about carbon, hydrogen, oxygen, nitrogen, the elements that make up your flesh. They're just elements. They follow the Schrödinger equation like everything else. So what makes you definite? What makes you have a specific position, a specific state, at any given moment? The standard answer is, again, decoherence. You interact with your environment so constantly and so thoroughly that your quantum superpositions decohere almost instantaneously. Before any quantum fuzziness can manifest, the environment has already measured you, collapsed your wave function, pinned you to a definite state. But Wojciech Zurek, the physicist who developed much of the modern theory of decoherence, is careful to point out that this doesn't solve the measurement problem. It just moves it. Because now the question becomes, what counts as environment? The air around you, the photons bouncing off your skin, the neurons firing in your brain. Zurek introduced the concept of unsettling, environment-induced superselection. The environment doesn't just randomly destroy quantum superpositions. It selects for certain states, what Zurek calls pointer states, that are stable against decoherence. These pointer states are the ones that survive environmental monitoring, the ones that leave consistent records in the environment, the ones that can be measured repeatedly and give the same result. In a sense, the environment is constantly measuring everything. Every photon that bounces off an object carries information about that object's position. Every air molecule that collides with it carries information about its state. These tiny interactions spread information about the object throughout the environment, creating what Zurek calls quantum Darwinism, a competition among quantum states in which only the fittest survive. The states that survive are the classical states, the states we see, the states that make up the everyday world. But this just pushes the question back one more step. Because the environment is made of atoms too. The photons that carry information about my position are themselves quantum objects. The air molecules are quantum objects. Everything is quantum. So why does it all look classical? And if the environment is measuring you, who is measuring the environment? The Schrödinger equation is universal. It applies to everything. So the environment should also be in superposition. So should the thing measuring the environment. So should the thing measuring that. This is sometimes called the von Neumann chain, after the mathematician John von Neumann, who first analyzed it rigorously in his 1932 book, Mathematical Foundations of Quantum Mechanics. Von Neumann showed that you can push the measurement event arbitrarily far down the chain, from the quantum system to the detector, from the detector to the amplifier, from the amplifier to the display, from the display to the observer's eye, from the eye to the brain. At each stage, entanglement spreads. The wave function grows larger, incorporating more and more of the universe. So where does it stop? Where does the wave function finally collapse? Von Neumann's controversial conclusion was that it might stop at consciousness. The human mind, he suggested, might be the final observer, the entity that actually causes the wave function to collapse. Without consciousness, the chain of entanglement would continue forever, and nothing would ever be definite. This idea was taken further by Eugene Wigner, von Neumann's friend and colleague. Wigner proposed a thought experiment in 1961 that has troubled physicists ever since. There's a famous thought experiment called Wigner's friend, proposed by the physicist Eugene Wigner in 1961. Imagine Wigner's friend is in a laboratory measuring a quantum system. According to the friend, the measurement has a definite result. The wave function collapsed. She observed the electron going through the left slit or the right slit. But from Wigner's perspective, standing outside the laboratory, the friend is part of the quantum system. She and the electron are entangled. They're in superposition together. The wave function hasn't collapsed. It's evolved into a state where friend observed left and friend observed right both exist simultaneously. Who's right? Does the wave function collapse or doesn't it? Wigner's original conclusion was disturbing. Consciousness must collapse the wave function. The friend's conscious experience forces a definite outcome. Without consciousness, nothing is ever real. Most physicists reject this conclusion. It seems to give consciousness a special role in physics, a role that goes beyond anything we can measure or test. It raises the specter of solipsism, the idea that only my consciousness is real, and the rest of the universe exists only when I'm watching. But here's the thing. No one has ever found a better answer. We don't know what consciousness is. We don't know how brains produce subjective experience, and we don't know where the quantum classical boundary lies. These questions might be connected in ways we don't yet understand. In 2020, a team led by Massimiliano Prietti performed an extended version of this experiment at Heriot-Watt University in Edinburgh. They used entangled photons to simulate Wigner and his friend, and they found that both perspectives are valid. The friend observes a definite outcome. Wigner observes a superposition, and both observations are correct. Reality, it seems, is not absolute. It depends on who's asking. This is not a metaphor. This is not philosophy. This is physics. So where does that leave us? What are we supposed to believe about the nature of reality, given what the Double Slit Experiment has taught us? Physicists have proposed many interpretations, ways of understanding what quantum mechanics means, as opposed to just using it to make predictions. And every one of them is terrifying in its own way. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, takes a pragmatic approach. Don't ask what's really happening. The wave function is a tool for calculating probabilities, nothing more. Before measurement, questions about the electron's position or path are meaningless. There is no deeper reality to uncover. Bohr was explicit about this. There is no quantum world, he reportedly said. There is only an abstract quantum physical description. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. But this leaves the measurement problem unsolved. If the wave function is just a calculation tool, what causes it to collapse? What makes measurement special? The Copenhagen interpretation draws a line between the quantum world and the classical world, but it doesn't explain where that line is or why it exists. The many worlds interpretation, proposed by Hugh Everett III in his 1957 Princeton doctoral thesis, takes the opposite approach. It says the wave function is real, completely, literally real, and it never collapses. When you measure an electron, you don't force it to choose a single outcome. Instead, the universe splits. In one branch, you observe the electron going through the left slit. In another branch, you observe it going through the right. Both branches are equally real. Both versions of you exist. Everett was a 26-year-old graduate student when he came up with this idea. His thesis advisor, John Wheeler, was initially enthusiastic, but urged Everett to present the idea in a way that wouldn't alienate the physics establishment. The original thesis was titled The Theory of the Universal Wave Function and ran to over 137 pages. It was cut down to a much shorter paper, Relative State Formulation of Quantum Mechanics, which appeared in Reviews of Modern Physics in 1957. The reception was brutal. Niels Bohr, the founding father of quantum mechanics, dismissed it. Wheeler arranged for Everett to visit Copenhagen and meet with Bohr, but the meeting went nowhere. Bohr and his colleagues were not interested. Everett, disappointed and perhaps bitter, left academia and never published another physics paper. He went to work for the Pentagon, doing operations research and game theory for the military. He died in 1982 at age 51, largely forgotten by the physics community. It wasn't until the 1970s that the many worlds interpretation began to gain traction. Bryce DeWitt, a theoretical physicist at the University of Texas, wrote a series of influential papers explaining and defending Everett's ideas. DeWitt coined the term many worlds. Everett had called it relative state or universal wave function, and the catchier name helped it spread. Every quantum interaction everywhere in the universe causes the universal wave function to branch. Every measurement, every decoherence event, every interaction between particles creates new branches. The number of parallel universes is constantly increasing, an exponentially growing forest of realities, each as solid and definite as the one you're experiencing now. You might find this comforting or horrifying. Everett found it elegant. His thesis advisor, John Wheeler, initially supported it, but later backed away, calling the multiplication of worlds an extravagance. The physicist David Deutsch champions the many worlds interpretation to this day, arguing that it's the only interpretation that takes quantum mechanics seriously. Deutsch makes a provocative argument about the double slit experiment. When a single photon creates an interference pattern, something must be interfering with it. That something, Deutsch argues, is the same photon in other universes. In his view, the single photon interference experiment is direct evidence for the existence of parallel universes. This is not a mainstream position. Most physicists find it too extravagant. But it's not easily dismissed either. The math of quantum mechanics is consistent with the many worlds interpretation. There's no way to disprove it experimentally. But there are other options. The de Broglie-Bohm interpretation, sometimes called pilot wave theory, proposes that particles have definite positions at all times, but they're guided by a wave that can pass through both slits simultaneously. The particle goes through one slit, the wave goes through both, and the wave tells the particle where to end up. This preserves determinism, but requires non-local influences. The particle's motion depends instantly on the state of the entire wave, no matter how spread out it is. The pilot wave theory was first proposed by Louis de Broglie in 1927 at the same Solvay conference where Einstein debated Bohr. But de Broglie couldn't answer the objections raised by Wolfgang Pauli, and he abandoned the idea. It was revived in 1952 by David Bohm, an American physicist who had been a protege of Robert Oppenheimer before being forced out of the United States during the McCarthy era. Bohm's version of the theory is mathematically complete and makes exactly the same predictions as standard quantum mechanics. In it, the electron in the double slit experiment really does go through just one slit. But the pilot wave, a real physical wave that guides the electron, passes through both slits and creates an interference pattern in its intensity. The electron, following the pilot wave, is more likely to end up in regions where the wave is strong and less likely to end up where the wave is weak. The catch is that the pilot wave responds instantly to changes in the experimental setup, no matter how far away. If you close one of the slits, the pilot wave changes throughout space immediately. This non-locality troubled Einstein, who famously called it spooky action at a distance. But we now know, from experiments testing Bell's inequality, that quantum mechanics is inherently non-local. The pilot wave theory just makes this non-locality explicit. Objective collapse theories propose that wave function collapse is a real physical process, something like gravity or electromagnetism, that occurs spontaneously when superpositions get too large. The Ghirardi-Rimini-Weber theory, for example, suggests that particles randomly collapse about once every 100 million years. For a single electron, this is negligible, but for a macroscopic object containing trillions of particles, collapses happen constantly, enforcing classical behavior. The GRW theory was proposed in 1986 by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber. It modifies the Schrödinger equation with a stochastic term, a random component that causes wave functions to spontaneously localize. The rate of collapse is said to be negligible for microscopic objects, but significant for macroscopic ones. The beauty of objective collapse theories is that they're experimentally testable. They predict small deviations from standard quantum mechanics, especially for mesoscopic objects, things that are neither fully quantum nor fully classical. Current experiments are getting close to the sensitivity needed to test these predictions. Within the next decade, we might know whether spontaneous collapse is real. The relational interpretation, developed by Carlo Rovelli, suggests that there is no absolute state of a system, only the state relative to another system. An electron's position is not a property of the electron alone, but a relation between the electron and whoever is measuring it. Different observers can have different facts about the same system, and both can be correct. Rovelli, who is better known for his work on loop quantum gravity, proposed the relational interpretation in 1996. It's inspired by Einstein's special relativity, which showed that simultaneity is not absolute. Two events that are simultaneous in one reference frame may not be simultaneous in another. Rovelli extends this idea to quantum mechanics. The state of a system is not absolute, but depends on who's asking. In the relational interpretation, there's nothing mysterious about Wigner's friend. The friend has one set of facts, Wigner has another, and both are correct relative to their respective perspectives. There's no need for consciousness to collapse wave functions, no need for parallel universes, no need for hidden variables. There's just information, and information is always relative to who has it. Each interpretation has its defenders and its critics. Each makes the same predictions for any experiment we can actually perform. Which one is true? There's no way to know. Quantum mechanics gives us the math, and the math works. What the math means is a question physics cannot answer. But maybe the question itself is wrong. Maybe we're asking what quantum mechanics tells us about reality, when we should be asking what it tells us about ourselves. Because here's what every interpretation agrees on. Information is fundamental. The observer cannot be removed from the picture. What you know, or could know, or choose to know, shapes what exists. In the Copenhagen interpretation, observation creates reality. In many worlds, observation splits reality. In relational quantum mechanics, reality is nothing but the information systems have about each other. Even in pilot wave theory, the guiding wave carries information about the experimental setup. This is perhaps the deepest insight to emerge from a century of grappling with quantum mechanics. We thought physics was about stuff, particles, fields, forces, but it turns out that physics is about information. What exists depends on what can be known. What's real depends on what leaves a trace. The physicist John Wheeler, who supervised Hugh Everett's thesis and spent decades thinking about the meaning of quantum mechanics, captured this insight in a phrase, it from bit. Everything, he suggested, every particle, every field of force, even space-time itself, derives its existence from the information theoretic answers to yes or no questions. The universe is made of information. This isn't just philosophy. Quantum information theory has become one of the most active and successful areas of physics. Quantum computers work by manipulating qubits, quantum bits that can be in superpositions of 0 and 1. Quantum cryptography uses the observer effect to create unbreakable codes. Any eavesdropper who tries to intercept a message disturbs it, revealing their presence. Quantum teleportation transfers the state of one particle to another by transmitting classical information and exploiting entanglement. All of these technologies are based on the central insight of the Double Slit Experiment. Information and reality are intertwined. You cannot separate what exists from what can be known about it. Zurich's work on decoherence and ion selection shows that classical reality emerges through a kind of Darwinian process. The states that survive environmental monitoring are the states that become real. The environment witnesses certain properties and not others, and those witnessed properties are the ones that exist for all practical purposes. This sounds mystical, but it's hard physics. It's in the mathematics. The Schrödinger equation doesn't care about our categories of wave and particle, real and unreal, definite and indefinite. It just evolves the wave function. What we call reality is what emerges from that evolution, what the math selects, what information propagates, what survives the constant measurement of the environment. And if that's true, then reality isn't something we discover. It's something we participate in creating. John Wheeler, in his later years, pushed this idea further than almost anyone. He proposed what he called the participatory anthropic principle. The universe only comes into definite existence because conscious observers measure it. We're not just observing a pre-existing reality, we're participating in its creation. Wheeler was not a mystic or a crank. He was one of the most accomplished physicists of the 20th century. Having worked with Einstein and Bohr, helped develop the theory of nuclear fission, contributed to the Manhattan Project, and made fundamental advances in general relativity. He coined the terms black hole and wormhole. When Wheeler talked about observers creating reality, people listened. In his 1983 paper, Law Without Law, Wheeler presented a diagram that has become one of the most reproduced images in discussions of quantum foundations. It shows a giant eye looking back at the universe, with the early cosmos emerging from the act of observation. The eye represents conscious observers, us. The diagram suggests that the universe and observers are bound together in a self-referential loop. We emerge from the universe, and the universe emerges from our observations. Wheeler called this the self-excited circuit of existence. The universe gives rise to observers through a long process of cosmic and biological evolution. Those observers then make observations that give the universe a definite past. Without observers, the universe would be a mere cloud of possibilities, never collapsing into the solid reality we experience. He illustrated this with his famous delayed choice thought experiment. Scaled up to cosmic proportions, imagine light from a distant quasar, bent around a galaxy on its way to Earth. The light left the quasar billions of years ago, but whether it traveled as a wave taking all paths or as a particle taking one path is not decided until we choose how to measure it, here, now, today. Our choice today determines what happened billions of years ago. We are not only observers, Wheeler wrote. We are participators. In some strange sense, this is a participatory universe. This idea has been extended by other physicists. Andre Linde, one of the architects of inflationary cosmology, has suggested that consciousness might be necessary for the universe to exist at all, that a universe without observers is a universe that never becomes real. Stephen Hawking and Thomas Hertog, in their final paper together before Hawking's death, proposed a top-down approach to cosmology in which the universe's history is determined by observations made in the present. These ideas remain speculative and controversial. Most physicists prefer to avoid questions about consciousness and stick to the mathematics of quantum mechanics. But the questions won't go away. The Double Slit Experiment keeps asking them every time it's performed. So what does this mean for you? For how you live your life, how you understand your place in the cosmos? You might be tempted to draw pseudo-scientific conclusions, to claim that quantum mechanics means consciousness creates reality, or that you can manifest your desires by observing them into existence, or that quantum effects in the brain give you free will. Be careful. These claims go far beyond what the physics supports. Quantum effects are real, but they're subtle. They operate at scales far below anything our brains or our intentions can access. The new age appropriation of quantum mechanics is based on metaphor, not measurement. The brain is warm and wet. Quantum coherence, the delicate superposition that allows interference, is destroyed almost instantly at body temperature. The neurons in your brain operate by classical electrochemical signals. Their behavior is well explained by ordinary physics. When someone claims that quantum consciousness lets you shape reality with your thoughts, ask them for the math. Ask them for the experiments. They won't have any. But there's a caveat. Some serious scientists, including Roger Penrose and anesthesiologist Stuart Hameroff, have proposed that quantum effects might play a role in consciousness. Their orchestrated objective reduction theory suggests that quantum coherence in microtubules, protein structures inside neurons, might be related to conscious experience. This is a real scientific hypothesis, though most neuroscientists remain skeptical. Even if it's true, it wouldn't mean you can influence external reality with your thoughts. It would just mean that consciousness itself might be a quantum phenomenon. The lesson of the double slit experiment isn't that you can think yourself rich or healthy. It's something more subtle and more profound. But there's a deeper truth here that doesn't require pseudoscience to appreciate. The universe is stranger than we imagined. The solid, definite reality we experience, the world of tables and chairs and people and planets, emerges from something far more fluid and uncertain. Underneath the surface, at the foundation of everything, there is only probability, superposition, entanglement. There is only information and its propagation. This is what 100 years of the most careful experiments have shown us. This is what the mathematics says. Reality is not what it seems. The world we experience is not the world that exists. It's the world that emerges from the interaction of quantum systems with their environment. Matter is not what we thought it was. The things we touch and hold and love are made of atoms, and atoms are made of particles, and particles are not particles. They're wave functions, probability clouds, patterns in an abstract mathematical space that only become concrete when they're observed. Think about what that means. The chair you're sitting in is not made of tiny solid balls called atoms. It's made of quantum fields, vibrating patterns of probability, held together by forces that are themselves quantum mechanical. The apparent solidity of matter is an emergent property, something that arises from the interaction of countless quantum systems, not something that exists at the fundamental level. You are not what you thought you were. You're a pattern of information, incredibly complex, constantly interacting with your environment, constantly being measured and collapsed into definiteness by the universe around you. The boundary between you and the world is not a wall. It's a conversation. Every photon that enters your eye carries information about the world. Every sound wave that reaches your ear carries information. Every molecule that touches your skin carries information. You are not separate from the universe. You are entangled with it in constant quantum interaction. And reality is not what you thought it was. It's not a stage on which we perform. It's not a container in which we exist. It's a process we're part of, a collaboration, a dance of observation and existence, measurement and manifestation, question and answer. The double slit experiment shows us this truth over and over every time it's performed. A beam of light, two slits, a screen. And the deepest question in all of physics: what is real when no one is looking? The answer, as far as we can tell, is nothing definite, nothing fixed, nothing final, until you look. 225 years ago, Thomas Young stood before the Royal Society and showed them a pattern of light and dark bands. He thought he was proving that light is a wave. He couldn't have known that he was opening a door to a completely different understanding of existence. Richard Feynman said that the double slit experiment contains the only mystery of quantum mechanics. But I think he was being modest. The mystery isn't just about how electrons can be waves and particles at the same time. It's about what kind of universe allows such a thing. It's about what we mean by existence, reality, truth. The experiment has been performed with photons, electrons, neutrons, atoms, and molecules containing thousands of atoms. It has been performed with delayed choices and quantum erasers. It has been performed in space, bouncing photons off satellites thousands of kilometers above Earth's surface, confirming wave-particle duality at unprecedented scales. Every time, the result is the same. When you don't look, matter behaves like a wave. When you look, it behaves like a particle. In 2025, scientists at MIT performed a new version of the double slit experiment using atoms trapped in an optical lattice. The atoms were cooled to near absolute zero and released, their positions limited only by the Heisenberg uncertainty principle. As single photons scattered off the atoms, an optical interference pattern formed and then disappeared as the atomic wave packets expanded and decoherence set in. The experiment demonstrated wave interference using nothing but quantum atoms and photons, pushing the boundaries of what we can observe. The double slit experiment has survived every attempt to explain it away. Generations of physicists have tried to make it make sense in classical terms, to show that there's some hidden mechanism, some overlooked factor that removes the mystery. All have failed. The experiments keep confirming the same strange truth. Observation matters. Information shapes reality. The universe is participatory. The universe, it seems, doesn't commit until it has to. And perhaps neither should we. Perhaps the lesson of the double slit experiment isn't just about physics. Perhaps it's about the hubris of certainty, about the danger of assuming we know what's real before we've looked closely, about the possibility that the deepest truths are not facts to be discovered, but questions to be held. There's a concept in quantum mechanics called complementarity, introduced by Niels Bohr. It says that some properties are mutually exclusive. You can measure position or momentum, wave behavior or particle behavior, but not both at once. The more precisely you know one, the less precisely you know the other. Maybe complementarity applies to human knowledge more broadly. Maybe the more certain we are about something, the more we're missing. Maybe the world is richer than any single perspective can capture. Werner Heisenberg, one of the founders of quantum mechanics, wrote, "The atoms or elementary particles themselves are not real. They form a world of potentialities or possibilities rather than one of things or facts. A world of potentialities. A world that waits. A world that becomes real only in the act of being observed. Niels Bohr said something similar. Everything we call real is made of things that cannot be regarded as real. The atoms that make up your body are not solid objects. They're clouds of probability. The forces that hold them together are exchange interactions mediated by virtual particles. The solid ground beneath your feet is mostly empty space, held together by electromagnetic repulsion between electron shells. And yet, here you are, reading these words, thinking these thoughts, as real as anything can be. This is the dark secret of the double slit experiment. Not that reality is an illusion, that's too simple, but that reality is incomplete. It's a work in progress. It's a collaboration between the observer and the observed, between mind and matter, between the question and the answer. You are not a passive witness to a pre-existing universe. You are a participant in an ongoing creation. Every observation you make, every measurement, every act of attention contributes to the definiteness of the world. The physicist Andre Linde once said that the universe is a self-observing system. We are not separate from the cosmos. We are the cosmos observing itself. Through our eyes, the universe looks back at itself. Through our measurements, it becomes real. The double slit experiment has survived every attempt to explain it away. Generations of physicists have tried to make it make sense in classical terms, to show that there's some hidden mechanism, some overlooked factor that removes the mystery. All have failed. The experiments keep confirming the same strange truth. Observation matters. Information shapes reality. The universe is participatory. Feynman said we should not ask why about quantum mechanics. We should just accept that nature is like this and learn to calculate. But humans are not content with mere calculation. We want to understand. We want to know what's really going on. And that desire to understand, that refusal to accept mystery, has driven science forward for centuries. The double slit experiment has resisted full understanding for 100 years. It remains a challenge and an invitation. Whoever finally explains it, whoever shows us what's really happening when a single electron passes through two slits, will have achieved something profound. Until then, we have the mystery. And the mystery is enough. 224 years after Thomas Young first shone light through two slits, we are still asking the same question. What is reality? And the answer we've found is stranger than anything Young could have imagined. Stranger than anything Newton or Einstein or Bohr or Feynman could have imagined. The experiment continues to be performed, refined, and extended. Scientists push it to larger scales, colder temperatures, more exotic particles. They use quantum entanglement and delayed choice and quantum erasure to probe every aspect of the mystery. And every time, the results are the same. The universe behaves exactly as quantum mechanics predicts, and exactly contrary to our intuitions about what should be possible. This is not mysticism. This is physics. And if that doesn't change how you see everything, if that doesn't make you look at your hand, your coffee cup, the sky outside your window with new wonder and new uncertainty, then you haven't understood what 200 years of careful experiments have been trying to tell us. The universe is not what you think it is, and neither are you.